So good evening everyone. So today we'll be um, going towards DC machines. So this where we try to realize the different or we started from basics, that what is required for continuous torque production, and then we went on to develop on that to realize the different machines. So to start with, we started with the realization of the stator magnetic field. So it could be stationary or rotating. We saw how to realize that if we inject a constant current in this type of structure, then we can have a stationary magnetic field. That will be the case for DC machine, as we'll see in a few minutes. And we went on to realize how we can have a rotating magnetic field generated by the stator. So we understood that if we have three phase winding whose axes are phase shifted by 120 degree in space, and if we inject 120 degree phase shifted current, that is balanced sinusoidal current, into all these windings, then we end up having a rotating magnetic field. Then we went on to see that whether we could produce that in some other way also. So we ended up with concentrated or distributed winding. So concentrated winding, the winding is wound around one pole, and distributed winding, the two sides of a coil are placed in two different slots. We also looked at some visual representations of that, and then we went on to see distributed winding for um, different slot numbers. First we started with a 6 slot machine, then we went on to see what happens if we have more number of slots, and we understood that we could reduce the amount of harmonics by going for higher and higher number of slots. Then of course we looked at uh, looked at another case, that is the 4 pole. Suppose in this case we had only one north pole and one south pole produced by the three phase distributed winding. Now for the same slot number, we went on to see that we could actually produce 4 poles out of the same thing. And if we follow the if we inject three phase balanced current into that, we can produce a rotating magnetic field. So you can see that this is one pole, this is the second pole, third pole, and 4 pole. So we could produce 4 poles. So we also understood electrical and mechanical angles by looking at time progression in the currents, and how the spatial electromagnetic field, the magnetic field, basically traverses along the ear gap. So we looked at that. Then we ended up having, or we came to the realization of the rotor magnetic field. So one case, how to produce a rotating magnetic field, that is very straightforward. That is, we inject some DC current into the rotor. So this is the magnetic field it produces when it is stationary, and if it rotates at the same speed of the stator magnetic field, it rotates at the same. The magnetic field produced by the rotor also rotates at the same speed. So this is the first case of first machine, that is known as synchronous machine. What is in synchronism? The rotor is in synchronism with the magnetic fields, basically the stator magnetic field, rotor magnetic field, both rotates at the synchronous speed, and the rotor also rotates at synchronous speed. That is why the rotor is in synchronism with the magnetic fields. So that is why it is called as synchronous machine. Now we went on to see the two different types by only changing the rotor. That is, we could have a cylindrical rotor, or we could have a Sellian pole rotor. So here I discussed about the permanent magnet. So if we replace the winding with permanent magnets, then we could potentially have the same thing, because permanent magnets are already magnetized, so there is no need to magnetize them from external source. So we could do away with the requirements for slip rings, which are required for in synchronous machine for injecting some current into the rotor. So we could do away with that. and yeah, and we went on to see discuss a few things about permanent magnets. So last that day, whatever I discussed, there was this minor there was a mistake in that, so I will just reiterate that so that there is no confusion regarding that. So this is the B, this is the H, these are the two axes. Now what do we mean by permanent magnets? Permanent magnets do not have any excitation. That means even without any external H, they have some remnant flux density which is quite significant, and if they experience some negative magnetic field intensity, then they demagnetize. So because H is negative, so they demagnetize, and the characteristic actually comes in the second quadrant. So there is something called, if we this coercive magnetic field Hc, basically minus that, because that is in the opposite direction, that is opposing the polarity of the magnet. So if that is applied, then the magnetic or the whatever is the magnetization is there, that gets lost, and it becomes a normal piece. So it is not there is no magnetic field, or the material becomes demagnetized at when some field equal to the coercive magnetic field is actually applied across it. Now question was, why does or why this negative magnetic field intensity actually come? So I started the case for a so I started with a simple case. So this is, say, a permanent magnet, say N and S, and there is some uh, uh, there is some external thing. Say we have an iron core which also has a gap. So this is the gap, and otherwise it is a continuous thing. So this is the ferromagnetic core, right, and it has some permanent magnet in it. So if we apply, so uh, and this case does not have any coils, that means it does not have any current injected anywhere in this magnetic structure. So if we take Amperian loop, if we take a Amperian loop, then there is no enclosed current, there is no currents enclosed by this Amperian loop, which I have tried to draw using red dotted line. So we have to apply, so if we apply Ampere's law, H dot dl, the right hand side will be I enclosed, that is equal to 0, right? Now this thing can be divided into three portions. You can see one portion we have the permanent magnet, another portion is the iron, that is ferromagnetic material portion, and the third portion is the small air gap. So if we divide it into three portions, then H magnet into L magnet, where L is this length. I think someone is unmuted. Unmuted, please mute yourself. Hm into Lm, plus, if the total iron length is Li and the H in iron is Hi, then it is Hi plus Li, plus whatever the small gap Hg into Lg, where Lg is this length, is equal to 0. Now for ferromagnetic materials, this H within ferromagnetic material is actually quite low. Why is that quite low? Because H is nothing but B divided by mu naught mu r, and mu r in ferromagnetic material is very high, whereas in air, for air mu r is 1, and for permanent magnets also mu r is somewhere very close to 1. It can be 1.03 to 1.05, something in that range. So for the, if we assume same flux density everywhere, then for the same B, whatever will be the H values in magnet and whatever will be the H value in the air gap, the H value in the iron will be very low compared to that. So the second term can safely be ignored. So we have Hm into Lm plus Hg into Lg equal to 0. So hm is equal to minus of Lg by Lm into Hg. So this is why if we keep a permanent magnet in a magnetic circuit with a small air gap, then based on the relative lengths of the gap and the length of the permanent magnet, there will be a negative field, because Lg and Lm both are positive. If we assume Hg sign to be positive, then the Hm has to be negative, as told by this equation. So as soon as we keep our permanent magnet uh, in any in environment, there is some negative magnetic field applied across it, and that is why it will slightly go in the negative direction. So H, if this is the plot for B magnet and H magnet, then Hm will go slightly negative, and it will have slightly lower B compared to whatever remnant flux density it had. It will slightly come below that, and it will operate there. So what happens if there is no air gap? There is no air gap in this case. If there is no air gap, then this term is not there. So this term is very negligible, but still some finite value it has. So in that case, Hm would have been minus of L, what is that, Li divided by Lm into Hi. Now because Hi is very low, so Hm will also be very low, so it will not get pushed much into the second quadrant, and it will operate very close to the y-axis. That is why it is always, if you have to maintain a permanent magnet, it is always best to put it inside an iron chamber or ferromagnetic material chamber, so that the magnetic field strength is retained. Otherwise, if you just put it in air, then air is a very some field with very high reluctance, so it will quickly get demagnetized. That is about that is a brief understanding about permanent magnets. And also we understood that at any point on this demagnetization characteristic, the magnetic energy that the permanent magnet can deliver is basically B into H, Bm into Hm. That is the magnetic energy that the permanent magnet can deliver to some other to some other uh, uh, magnetic circuit. So this is about it. And another thing, how to decide, how will this operating point, suppose it is there, uh, some air gap is there, or we have to use the permanent magnet for some permanent magnet machine, then how to estimate, while designing, we have to decide that where this permanent magnet, what will be the operating point this permanent magnet will operate at. This thing can be just, we can have some brief calculation. So if we assume that there is basically the same flux has to go through this, right? So if we so whatever flux is going through the permanent magnet, going from the permanent magnet, that same flux goes to the air gap also. And if we neglect fringing, that is, in the air gap, flux will fringe flux lines will fringe in the both directions. So if we neglect that and assume the cross sectional area to be uniform everywhere, then B magnet into A magnet is equal to B gap into A gap, right? So we have basically two equations. This becomes one equation, and another equation, if we write H mag M into Lm equal to minus of Hg into Lg. This becomes our second equation. So this Hg into Lg is nothing but the equivalent. It is here like this, but uh, for a specific case also it can be derived. So if we divide 1 by 2, then what we have? We have Bm Am divided by Hm into Lm is equal to minus of Bg Ag and Hg Lg, right? So I'll remove some portion from it. Yes, so Bg by Hg, this thing is nothing but mu 0. So Bm into Am divided by Hm into Lm is equal to minus of mu naught into Ag by Lg. So if we take it in one side, Bm by Lm is equal to mu naught into Ag into Lm divided by um, Am into Lg. Now if we take this approximation that Ag, that is the air gap equivalent area, is approximately equal to Am, then this goes off, and we have the Bm by Hm ratio to be equal to minus of mu naught into Lm by Lg, right? So it will so Bm versus Lm, if Hm, if we plot, then it is a straight line that passes through the origin, and it has negative slope. That means it is something like this, where this slope basically depends on the this ratio, whatever this whole thing is. This is actually this ratio, and this thing, if I rewrite, then Lg, if it is taken up, basically uh, or Lm by Am can be written together, and Lg by Ag can be written together. So Lm by Am, that is nothing but that is proportional to the reluctance of the magnet, and Lg by Ag, that is proportional to the reluctance offered in the air gap path. So this ratio decides what will be the slope of this line. So if you can think, if there is no air gap, that is, this ratio goes to infinity, because it's negative infinity or infinity basically, so it is along y axis. If it is predominantly so this lower ratio is very high compared to uh, the upper ratio, then it is a very low number, very small number. So very small number suggests that slope will go very close to this will go to very close to 180 degree, because it's negative, so it will demagnetize in some time. So this is about some basic brief discussion on permanent magnets. So I hope it clarifies whatever uh, whatever doubt was raised in the group. Is there any question regarding this part?
Sir, what does from graph it is clear that if we apply minus Hg, the remnant flux in the permanent magnet will become zero. That's fine. But
Yes.
what about the expression we are getting and equating it to zero and getting negative thing?
Which one? This one?
No, sir. Which we have erased previously. You have discussed that thing.
So there I was I
Minus
was applying
HGLG by
Maxwell's
H.
circuital law.
Yes,
I was
correct.
applying Maxwell's circuital law here, right?
Yes, sir. Yes, yes.
So Hm into Lm plus H iron into L iron plus H gap
HG.
into L gap equal to 0, right?
Correct.
So that is
Yes.
Maxwell, this Ampere circuital law, nothing
Yes, sir.
other than
That's
that.
clear. That's clear.
uh, Next.
But do you mean that if by taking some means of coil and applying some means of, by injecting some current, such that we are getting minus HG by Lm of magnetic field intensity that will make our flux produced by the permanent magnet equal to zero.
uh, that is one way. Or if we do not do that, if we simply keep the permanent magnet in some circuit where there is some air gap, then air gap will inherently oppose that, because if you write this
Okay.
equation whatever I have written here, H
Yes.
iron I have told why to neglect it, then Hm came out to be minus of Lg by Lm into Hi. So this was our equation. So that means, or basically gap. So that tells you that if we make our permanent magnet face any small, even a small air gap, then the
Yes.
reluctance of the small gap, whatever, because some flux has to flow through this gap, then because of that whatever H drop will be there in this small air gap, that will oppose the permanent magnet. So that will act as the negative H across the uh, permanent magnet, and that is why whatever flux density it had, remnant flux density, it will come down little bit and operate at that point.
Okay,
So
that's
it
fine.
depends what is the air gap we expose our magnet to. And next
Yes.
question is very interesting actually. What happens if we have some coil? Say what happens we additionally have some coil, and if we inject current like this, then this will, if we look at its own field, then it will oppose this one, right? This will oppose the field produced by the magnet. Now what happens in this case? Now if we apply this Ampere circuital law in this case, where we have some added current flowing into that, if we consider number of turns to be n, then say it is Ni of mmf, Ni of current which is there. Now now we are traversing the loop in this direction, right? If we have current like this, that will make the flux flow in the opposite direction. That means whatever enclosed current is there, that will be, in this case, will be minus of Ni. If I consider DC current, then it is minus of Ni. Now with the same assumptions, if we go ahead, then we will have Hm is equal to minus of Lg by Lm into Hg minus Ni divided by Lm. So that means if we plot this thing, if we plot Hm, or uh, if we try to plot that, then there is some shift here, there is some negative shift here. That means the our this line, so earlier I simply drew that line. So in this case there will be a inherent negative DC shift because of the current, which will demagnetize it up to a certain value. Then beyond that, this slope is anyway decided by uh, whatever Lg by Lm, or in this case actually we should we cannot start applying from this. We have to do this math whatever I have done, divided by 1 by 2, all the this thing. If we this equation, this uh, equation inside box, if we apply, then you will see that there will be an additional DC term, there will be additional DC term, some H0, which is related to the ampere conductor that we are putting. So now if we plot this Hm versus Bm versus Hm in this line, then there will be a intercept in the x axis, that is nothing but this thing H0. So our load or our this line is actually known as or termed as load line. So magnet has its own demagnetization characteristic, and load line is based on the circuit it supplies flux to. So if there is no excitation in that, if there are no conductors, then this will be our load line which is passing through the origin with certain slope. Slope depends on this lengths of the gap and length of the magnet, etc. If it has some if it has some demagnetizing mmf produced by some current, then this line will no longer pass through origin, but it will be shifted in the leftward direction. So it will be like this, the red line that I have plotted. So for the same gap, for some current which will decide this H0, this will operate at some other operating point, and obviously you can see that it will get demagnetized more, it will be more demagnetized. So this is what happens if you uh, pass demagnet, or if you pass some current that opposes the field of the permanent magnet, then it gets demagnetized further.
Okay, thank you for the clarification, sir. Sir, I have another doubt.
Okay.
Sir, from the expression we have derived without any that coil,
Yes.
HM is minus LG LM HG. Sir, if I increase the LG such that it is more, does it
Yes.
mean that the flux which is given by permanent magnet in the north to south will become in opposite direction just because of increasing the air gap?
No, no, no. By increasing the air gap, it will not. But if we do not have any excitation, it cannot become opposite. It will
Okay.
reduce, like this slope, whatever this line is there, its slope will increase more and more, but it cannot go to third quadrant. It will remain in the second quadrant only, because even if L is you can see this expression, right? Even if this expression, this ratio is very close to 0, that means Lg is very very high compared to Lm, and whatever this Ag into Lm is very very low compared to Am into Lg, then this one is tending to 0. So minus 0 means it is actually like this, along the negative x direction. So it will get demagnetized completely, but it will not, it will, unless you have another field, it will not make the flux flow in the opposite direction.
Thank you, sir. Thank you for the clarification. And another thing, you have said that we place in ferromagnetic material in applications. Why? What's that need, sir?
Because unless you place your permanent magnet within some ferromagnetic material, then there will be a lot of air gap. it will
Yes.
it will it will keep on giving flux, and if you have lot of air, if the flux has to flow through air, that means this ratio this ratio will be very low. That means the load line it sees will be very uh, will be having very low slope. That means it will get demagnetized quickly, or it will operate at very low flux density, and it will soon get demagnetized with time.
Okay, you are saying that to get the desired flux density, we are keeping it in ferromagnetic material with
No, no, no. I
specified
am
air
saying
gap.
that to retain its magnetic field, whatever remnant flux density it has, to
Yes.
retain that, because we
Oh,
are not using the permanent magnet that time. We are just storing it. In order to store it, we have to uh, make it. We have to keep it inside some ferromagnetic chamber.
okay. Okay,
Yeah,
sir. Thank you.
yeah. So we'll go ahead.
Yeah, and I
Then,
have one question, Samrat.
okay.
So the manufacturer data sheet, how it will look like the load line, because they will not
No, no,
know
no. Load
what the
line
air
is
gap is.
based on the circuit or the application that you are putting the permanent magnet into. So it depends on you. It will not, load line will not be there in the manufacturer's datasheet. Manufacturer's datasheet will provide this demagnetization characteristic.
Okay, okay. Thanks.
Load line is based on you, based on your indication. You have to design that.
So suppose if I
Okay, so
want
yeah.
maximum energy from this curve, I have to operate the center for maximum BNH.
Sorry, I could. Its sound is
For
quite low. I
max
could not see
no
hear you.
for the maximum energy to avail
Yes,
from the magnet, we have to operate in the center of the curve, the
yes,
third quadrant.
yes. So if it is a straight line, then yeah, it is the center. It is the it is this point that is the that will uh, enable maximum energy transfer or maximum energy, magnetic energy flow from the permanent magnet to our external circuit. Yeah, but it will have to be chosen judiciously so that it does not go. There is always a limit that you cannot you should not operate your B beyond certain below certain B, say B min, which will increase its chances of demagnetization quickly. So there is about health. This is only the physics that I have explained. Additionally, there will be health issues that your permanent magnet should not be demagnetized up to this much. Then it will get its life will be very shorter. So all those issues will come in.
Okay, okay, sir.
Okay. So yeah. So we discussed about permanent magnets. Then we went on to see the second case. We saw that if we inject some AC current into the rotor, then we have some rotating magnetic field produced by the rotor with respect to rotor. Now if rotor is stationary, that rotates at that speed, and if rotor is rotating, that magnetic field speed actually uh, gets added with the rotor speed to get the net magnetic rotor magnetic field speed with respect to the any stationary observer. Now if we choose uh, rotor speed and current appropriately, then we saw that we could match the rotor magnetic field speed and stator magnetic field speed, which meant that we could have uh, continuous torque production. Then we understood our flux linkages and understood that there is actually no need to put conductors in the rotor, and we could have, if we simply excite the stator, then there will be, because of this electromagnetic induction, there will be some flux linkages, varying flux linkages that will cause varying induced EMF, and that will if we short them, if we make the current paths come closed, then there will be some current flow. So there will be current in the rotor winding automatically because of electromagnetic induction. So there is no need to separately, no necessity I should say, to separately excite the rotor also. uh, and we went on to see that we could actually have this induction machine, this second type of machine where the rotor is actually not rotating at the same speed as the stator magnetic field or rotor magnetic field, that is known as asynchronous machine or induction machine, because it operates on the principle of electromagnetic induction. Then we went on to see that okay, we could inject some current into the rotor, or we have the option, or we have the option not to inject any current into the rotor. And if we are not injecting any current, why to go with manual winding, why to wind it manually? We could go with cage rotor, where there will be some bars, and the bars will be short circuited from both sides. So if there are some bars like that, all those bars will be short circuited on the two sides, and this could be the structure of the rotor, which is known as cage rotor. Then we went on to discuss about uh, cage rotor, what happens in the different bars if we excite the rotor, excite the stator. Basically, we have some magnetic field produced by the stator, and we saw that there are the flux linkages. If we have n bars in the rotor, then the flux linkage waveforms in the two subsequent bars, they are basically phase shifted from each other by 360 degree divided by n. if there are n number of bars. So n is the number of bars. So this is the case for a two pole machine. For in four pole machine, obviously it has to be multiplied by p by 2 to get the angle displacement between flux linkages, the phase shift between flux linkages seen by two subsequent bars. And if we have this many bars, then or if we have flux linkage like this, the corresponding induced EMF can be obtained by the just giving them a phase shift in the positive direction by 90 degree. So this is another thing. So you can at this point probably you can understand that it is something like we discussed in the beginning, right? We could have three phase we could have three phase axis phase shifted from each other by 120 degree, or we could have, this is three phase, or we could have n phase shifted from each other by 360 divided by n, where n is greater than 2. So this is this different bars. If we consider the diametrically opposite bars to be one corresponding to one phase, then you can see that it is the case, actually case for whatever, if n is the number of bars or nb is the number of bars, nb divided by 2, it is the case for nb by 2 phase excitation, because nb by 2 phase, so this is one phase whose axis will be somewhere here, then the next phase will be here, its axis will be phase shifted. Similarly, there are nb by 2 phases, and nb by 2 phases are excited by phase shifted currents, appropriate phase shifted currents. So that also produces the same magnetic field. So basically, if we have nb by 2 phases phase shifted by or basically excited by balanced currents of these many phase numbers, then that thing also produces a rotating magnetic field based on the frequency of the current excitation. So our cage rotor is something like that. Now there was a question regarding the confusion between the direction of magnetic flux and magnetic field. So I'll like to uh, uh, so there is, probably I'll explain here. So you have so magnetic field. So if we have magnetic field, just consider as a bar magnet. So we have north pole in some direction and south pole in some direction. So if we have north and south like this, then the flux direction is fixed. There is no convention in that. It will start from the south pole and it will go towards the south pole. Uh, in the externally, and internally it will go from south to north. That is about the flux direction. There is no confusion or about nothing to do with convention here. Now if we have to define the field direction, we have two choices. We could either define the field as some arrow from south pole to north pole, or we could also have some convention where the field direction will be south pole, north pole to south pole. That is completely based on our assumption or our convention. Say we choose one of them. We choose, say, south to north, as the case. Then for the other case also you have to stick to that. Now you can see that stator, say, this is the north pole, this is the south pole. So we have to if we have to assign the field direction, then it has to be north to south, or here what are we taking, let us take the second one, because that is what we have taken in this case, north to south. So let us take the north to south case. So this becomes the stator field direction. Now for the rotor, we have understood the currents, the rotor currents. We have understood the flux, rotor flux direction from that. if we have understood the rotor flux direction, then we have understood the polarities, that is which one is north and which one is south. Just to reiterate, this is dot, so flux will be in this direction. Now if we look at the rotor surface, then from the rotor surface on this side the fluxes are coming out radially. So this side has to be north pole, and the opposite side, because flux lines are coming in, so on the surface flux lines are entering, so it has to be south pole. Now as soon as we have given north pole and south pole polarities in the rotor, now following the same convention that we have taken for field direction, it could be anything also, it could be opposite also, but we have just taken a convention that field direction will indicate by some arrow which is from north to south. So if we follow that, what is there, if we follow that, then north to south, this becomes our rotor field uh, rotor field direction. So from this you can see that in this case stator field, because rotor is rotating in the anti-clockwise direction, so stator field is actually leading rotor field. Both are rotating anti-clockwise direction, so stator field is ahead compared to the rotor field. So does this answer your question?
Yes, sir, clear. Thank you.
Okay. So we went on to see the two cases. We went on to see the cases for different time instants to understand it clearly, and that the stator field is rotating in the anti-clockwise direction and the rotor is also following it, lagging it by 90 degree. So we understood the motoring action. Then we briefly looked at the end ring currents, how to calculate that. We saw that we just had to apply KCL at all the nodes where the bars are joining the two segments of the end ring. So if we indicate something, indicate some direction, and say this is I bar 1, then we could apply some KCL, we could apply KCL at all these nodes to get the currents, and we could solve those to get the IE and end ring segment currents. And the last equation, how to get that, we could, if this is our end ring that has got different segments, we could apply KVL in this loop, and if the resistances are exactly equal in different segments, then it boils down to summation of IEN, that is equal to 0. So from this, whatever number of bars are there, we have the same number of equations, and we could solve that in order to find the different end ring currents for a given instant of time. And that same thing can be done for different instants of time, and we could have uh, current waveforms in different end ring segments. The next we looked at the generation case, where the rotor is actually rotating at higher speed compared to the stator magnetic field rotation speed. So that is actually we have taken 3600 rpm. So what is happening? Well, we saw that earlier whatever is the phase sequence, this time phase sequence got reversed. What is the effect of phase sequence reversal? If for phase sequence 1 the rotating field was in the anti-clockwise direction, for phase sequence 2 it will be in the it will be in the clockwise direction. So we had this case, say this is the rotor. Rotor is already rotating at some speed. Now with respect to rotor, the field, earlier it was rotating in the same speed, now it is actually rotating in the opposite speed. If this speed is higher, say 3600, and as in this case, and the induced EMF frequency will be 600 or 600 rpm or 10 hertz, So 600 rpm rotating field with respect to rotor will be in the clockwise direction because the phase sequence is opposite. So with respect to a stationary observer, that magnetic field actually rotates at 3600 minus, because the direction is opposite, minus 600 equal to 3000 rpm. So that's all. So that maintains our case that the speed of stator magnetic field and rotor magnetic field with respect to a stationary observer has to be same. So for generation, that is realized by uh, or that gets realized by having the phase sequence in the rotor opposite compared to whatever is the phase sequence in the rotor for the motoring case. So this also we have seen for different instance, and we saw that if we follow the same thing in this case, if this is the stator magnetic field direction, we are taking direction from north to south, then for the rotor, if we take the same north to south, then you can see in this case fr is actually leading fs, because direction of the rotor is still the same. Now you can see that fr is actually leading fs. So that is what is telling you that energy transfer now happens from the rotor to the stator. That means generating action. Now we looked at it at different instance. Now we come to the most complicated machine, apparently the most complicated machine, uh, because synchronous machine for me to explain you just took some 2-3 slides. That's all, or even one slide, that is enough. That we are exciting something in the rotor, we are making it rotate at the same speed. So we have a rotor magnetic field that rotates at the same speed as the stator magnetic field. So that is done. For induction machine, okay, it took a few more slides, some complication is there, but eventually we could have uh, two magnetic fields rotating at the same speed. Now it may look the simplest, but implementation wise it is the most complicated. So in this case, what we have, DC machine stationary magnetic field, how to produce, we already know. We have some stator coils, we inject some DC current into that, dot cross, there will be some magnetic field, magnetic flux will be flowing like this. So you have uh, flux going upward in the top side, uh, upward in the bottom side also, but radially outward in the upper side, radially inward in the negative side. So uh, we had some north pole, we have some south pole here on top and north pole here on the bottom. Now what can we do? We can put some conductors, we can put some magnetic fields in the rotor. We can basically make some slot in the rotor like this. Say we have made how many, 1 2 3 4 5 6 7 8 9, so total 18 slots we have made. And say at any given instant of time, when the rotor is stationary, we inject positive current or dot current into all the slots which are on top, and cross current in all the slots which are in bottom. So at this given instant, all these are dot, and all these bottom ones are cross of the same magnitude. Earlier when we saw for the rotor bars, it was currents of different amplitudes in different bars, but in this case in all different conductors are having the same current. So if we have current like this, then what will be the magnetic field direction? Magnetic field direction will be, or flux direction will be like this. Flux direction will be like this. So you can see that we have two magnetic fields. One is this. So if this is stator, we have if this is a stator north and south, Then assuming north to south, this is the stator magnetic field. Now if we have rotor flux like then this side it is coming out, so it will become north. I'll use some other color. This will become north and this will become south. So following the same convention, this is north to south. So this is like this, right? So this is the so we have two magnetic fields which are basically in quadrature in 90-degree with respect to each other. Then will there be torque? Yes, there will be torque, and it will rotate, right? It will rotate in some direction. So we could have torque production. But what is the complicacy here? As soon as it rotates, say this was our current directions. Now as soon as it rotates by some angle, whatever, say this is conductor 1, this was conductor 18. Suppose it rotates in the anticlockwise direction. This conductor 1 comes here and conductor 18 comes here. Now conductor 1, whatever current direction it was conducting, it remains the same. It is positive only. It is dot only. But conductor 18, earlier it was conducting current in the cross direction. Now it has to conduct current in the dot direction. So that means there has to be some flip. There has to be some flip in the coil current direction with rotation. And with rotation, the same thing has to happen for all the coils. For all the coils, we have to have flipping of the direction after as it crosses this boundary between the two poles. So this is, if these are the two poles, then this is the interpolar axis. As soon as some coil crosses the interpolar axis, its current direction has to be flipped. Now the rotor is rotating. That means the conductors are also rotating. How to flip this current direction? That is a very complicated physical constraint or physical problem. How to flip these current directions. And I cannot discuss how that is done unless I discuss how these windings are connected and how these winding terminals are terminated in something which is also rotating and which are in contact with something which is apparently stationary. So this takes us to all the complicated things which are there in the DC machine, like you have something stationary or situated on the shaft itself, some ring like this, segmented ring, and all these lines that I have indicated, those are insulation. That is, two subsequent segments are disconnected from each other. So all the terminals, coil terminals, they are basically coming and getting connected in one or more of the segments. Now this is rotating, so the coils are rotating, the commutator segment is also this commutator ring is also rotating, so everything is rotating here. So this is a mechanically stable thing, everything is rotating, so no problem. But we have to take the connection outside also to the stationary world. For that, we can have two or more connections like this, and we will have terminals coming out from that. So here it will be current of the same direction only, and this because this commutator will keep on rotating, so sometimes, so it will be the coil direct coil connection and other things will be done in such a way that this constraint that we are having, that as soon as some coil crosses the interpolar axis, its current direction has to flip. So this will be maintained by this type of structure, but I cannot discuss this unless I discuss little bit about winding and how this winding is done for DC machine. So eventually I will discuss that. After that this will become very evident why or how that is happening. So yeah, so that is about the DC machine. Now suppose this happens, and at any given instant of time, all the conductors which are in on the top side are having dot polarity, and all the conductors which are on the bottom side are having cross polarity. Then we have we have a flux direction like this, and we have two magnetic fields which are at quadrature. So that is, we have seen, we have discussed that if torque is basically F1 into F2 into sine of delta, where delta is the angle between the two magnetic fields, then in order to maximize torque for two given field magnitudes, then we have to maximize delta at 90 degree, that is when sine delta will be 0, sine delta will be 1. And if delta is 0, then sine delta is 0, so that means the two magnetic fields are aligned. That means there is no torque production. So we can have, if we have this type of structure ensuring all the things are happening correctly, then we could actually have a case like this, where all the dot conductors are there on the top and cross conductors there on the bottom, and we'll have uh, we'll have
Maximum torque
continuous
at
torque
every
production.
instant.
Yeah, maximum constant torque and maximum possible torque that is possible for the given F1 F2. And we could have constant torque, constant steady torque. Yes, so I have just indicated uh, how the field will look like if both the fields, both the field coil and the armature coil, both are excited with some current. Then I have indicated uh, how the flux line distribution will be, and you can see that in the rotor it's like, so earlier axis was like this is the stator axis. Now rotor axis is also there, which is whose axis is 90 degree shifted. Now the net magnetic field will be tilted in some direction because these two are vectors, because some magnitude directed at certain angle, so both are vectors. And based on the relative magnitude and angle, there will be a relative vector, which in this case is like this is the resultant, not relative, some resultant magnetic field, and you can see that it is tilted. And we'll look at this case in detail, that okay, what is happening in the case of a DC machine. But we can see that one side of the stator pole, the flux density is increasing. You can also look at the color plot, where you can clearly, so blue indicates the lowest flux density, green at the middle mid flux densities, and red or orange the maximum flux density. So you can see that on one side of the stator pole you have higher flux density compared to the other side, and same thing happens in the diametrically opposite side of the stator pole show. So one side it gets uh, stronger, another side it gets weaker. So because of that there is a torque production, and this can simply be put like this. So if it is south pole, because flux lines are like this, so they are leaving the stator surface. Here it is, so now north pole, because they are entering the stator surface. Here for the rotor, they are leaving the rotor surface here. So north pole is here and south pole is here. Now you can see that this north pole will get attracted like this, and south pole will get attracted like this. So there is a torque in action which makes it rotate in the anticlockwise direction. Uh, this is about the DC machine, the magnetic field. Uh, Probably I'll stop for questions now if there are any questions.
Sir, can you
Then
go
I'll,
back
yeah,
to 33 slide number?
33.
Yes, sir.
Okay, is there any other question in nearby slides or regarding DC machine, whatever I have discussed? Okay, then probably uh, I'll go to 33. Yes, 33.
Sir, here we thought of flux density will be having a constant magnitude which revolves in the space, right?
Yes, ideally.
Yes,
Ideally,
but
yes.
when we look at the plot which you have shown with angular position b radial,
Yes.
when we are shifting with respect to time,
Uh,
it is not the waveform is a bit changing, sir. I observed when you are going through the slides.
okay.
Could you run once?
So you are telling, you are mentioning about this change, right? Now it
Yes,
is almost the same here.
yes,
Now
yes,
if I go to
correct.
the next instant, you see some peaky type of a thing, right? Like, right,
Yes,
this is what
yes,
you
sir,
are
correct,
pointing at.
correct, correct,
Yeah,
correct.
so actually if you do the distribution, or you plot the mmf distribution that I have indicated in uh, some lecture, how to plot the mmf distribution. So for a given uh, current excitation, if you take
Yes, by
different
taking ampere loops kind of thing.
ampere loops like this,
Yes,
then you could plot the this mmf distribution at different. So for mmf distribution at this given instant, and then same thing if you repeat for other time instance, you will get uh, the mmf distribution. So basically mmf as with theta for different time, right?
yes, correct,
So
correct.
that you will get, and that if you plot, you will see that for certain time instance there will be uh, a peaky thing, that whatever you are pointing out, at some instance there will be that, and some instance there will not be any such peaky thing. And actually it will not shift as abruptly that it seems in this animation, because you can understand that I am only doing it at
Discrete
multiple
points.
discrete points, right? I am
Correct.
doing it for 0, then what is the next? Yeah, so I'm doing at some discrete points, so
Oh,
it will not be as discrete as it looks. But yeah, this comes directly from the mmf distribution. In the mmf distribution, if you draw, then you will see that actually this type of thing will come, and actually it is normal, right? You expect the mmf distribution to be sinusoid.
yes, correct, sir.
Sinusoid will have some peaky thing at the middle.
Yes,
So same
correct.
sinusoid can be realized in two ways. Say some instance there will be no peaky thing like this, or some instance there will be some peaky thing. So Some instance will be like this, and some instance will be uh, the opposite way. But it is directly coming from the MMF distribution. So actually, it will be like that.
Okay. What I thought is like it will be a constant wave moving from 0 to 360, but it is not
Yes.
that.
Yeah. Ideally, it is a constant thing, but
Okay.
because you are not ideally it will be constant amplitude you uh, if you have no slottings. If
Okay.
you have no slottings, it is everywhere cylindrical, everywhere equal, so there will be no notches. So you will
Oh,
have, and why these steps are coming because you are
because
not,
of the slots.
because you are putting currents concentrated in certain slots.
Yes,
if
sir.
you
Correct.
distribute the if you distribute the current, whatever is discussed in your textbooks, like some copper sheet, where the current is uniformly distributed as sinusoids. So instead of this copper, discrete coppers at multiple locations, you have uniform copper and distributed, or current, or sinusoidal current flowing through that. Actually, the bar case that we have seen, that is very close to that, where we have, here what is the constraint? Can you understand that? Here we are putting two phases of R phase,
Yes.
because these two coils are connected in series. So whatever current one flows, one conducts, the current to the other thing also has to be the same. But the beauty about bars is there is no such constraint. So this can have its own independent current, and this can have its own independent current. I am talking about two subsequent positions.
Okay.
So for the bar case, if you see, then it will be closer to a sinusoid, because it's closer to ideal assumptions.
Okay.
Because
Sir.
this discrete is coming because we are concentrating the conductors in
Okay.
different discrete slots. That is right.
Okay. Sir, one more thing. Like you have answered the question, given the answer for why we are having dips
Yes.
in the 33 slide.
Yes. Because of the slots.
Yes, sir. But at the same time, before the dip, we are having some peaky nature, if I observe.
Yeah, we are having some peaky nature also. Now what is happening? So if I try to,
Immediately after the dip, we are having the peaky nature.
yeah. So ideally, if we have a cylinder like this is a surface. This is a cylindrical surface with
Yes.
no slotting, etc.
Okay.
Then if we have the flux distribution, they will be uniform,
Yes, sir.
right?
Yes, correct.
Now now if I, let me draw a few more things, right? So this is like our cylindrical surface which we had. And if we now we have the same geometry, right? So here at the middle, because almost it is there is no discontinuity, so almost the same flux density that it was supposed to have, it will retain that, right? It will
Yes, sir.
retain that.
Yes.
Now what will happen at the middle? Whatever flux was supposed to flow in the slot region will get diverted and flow like this. And additionally, this portion was anyway normally was supposed to flow some flux, so that flux
Yes.
will be there. And additionally, whatever flux was supposed to flow in the slot opening portion, that will also get diverted into these two edges,
Okay. Okay.
to these two edges. So
Yes.
because of
Yeah.
that, at the
Oh,
two edges there will be higher flux density compared to whatever you have in the tooth main tooth body portion.
yes.
So
Yes.
tooth
I
body
see.
portion you will have flux density whatever you would have for a cylindrical surface. That is
Okay. Okay.
same. That is a stepped type of a waveform. Whatever you would have if you did not have any slots. But
Yes, sir.
because of slots, in the slot opening portion, flux densities will reduce. That
Yes.
flux has to go somewhere. That will go
Yes.
to the
Yes.
nearby teeth openings, and those
Okay,
teeth
sir.
openings anyway had some flux, so they will get added up, and that is why is you are getting these notches
Okay.
at the two edges everywhere. You can see that is a very deep observation, I must say. By looking at that, yeah, I would like to congratulate you for finishing all the lectures by this weekend and also attending this live class. Yeah, well
Thank you,
done.
sir. Thank you. Sir, can I say in this way such that the flux is choosing the lower reluctance path?
Yes, yes, yes. That is the property of flux lines. They will
Okay.
always choose a minimum reluctance path. Accordingly, they will distribute themselves.
Okay, sir. Thank you. Thank you so much.
Yeah.
Then the last slide, 63, I think.
63.
The last, like,
63. Yeah.
next next
Okay.
the FEM simulation. Yeah, here
Yes.
we have two fields which are displaced by 90-degree, and the
Uh-huh.
vectorial addition we are getting the resultant field, correct?
Yes. Yes.
So the same case is applied to the synchronous machine, induction machine. There are two
Yes.
fields,
Yes.
and the two fields will have a resultant flux density. What is the
Yes.
consequences of that resultant flux density? What it
So
will do?
resultant flux density will actually cause torque. So this we will see step by step for DC machine, because if we understand for one case, because it's the same thing, two fields which are coming producing some resultant field, we will see that one field does not produce any torque. Two fields, the second field on its own does not produce any torque, but the two fields, because there is some resultant field, that will produce some torque, net torque. How that happens, we'll look at that step by step
But
for
we
DC machine.
but we already discussed the torque is proportional to the uh, magnitude of the field strength multiplied by the cos of the angle between them.
Yes, yes, that is in a
Well,
gross sense, but what happens in a local point to point at different points on the rotor, and actually there will be force, there will be local force distribution that will add up to get the torque. So torque in a gross sense is like this. Torque in a gross sense is like this. Some force is happening acting in this direction, and some other force is acting in this direction. This is a couple. So if this is F1, this is also F1, and this is the distance. So F into distance, this is the torque. That is our regular understanding about torque. But in actual case, all these three cases, we will look at the case for a DC machine, and the same thing will follow for other machines also. We would see that this torque is not as simple as that, not as simple as two forces acting on two diametrically opposite side, and we have some couple. There will be a number of forces acting at different tooths, which will in its net effect will produce that torque. So although this information, this thing, this torque is proportional to F1, F2 and sine delta. That is a gross expression that does not tell you anything about the force density distribution. Where is uh, where how much force is acting in different portions of the motor or stator as well as rotor. So that information can be only understood from the field distribution, and we will look at that, and from there we will come to torque.
Okay, okay.
How this distribution of force. So next we will look at force distribution on different parts of the motor, and that will lead us to some torque. And why this
So
force
anyway,
distribution is also important, because torque only makes the rotor to rotate, but this force we will see what is this force is in the tangential direction. But we would see that in any electrical machine there is a very much stronger force that does not participate in torque production, but that is there, and that actually produces uh, phenomena like vibration, acoustic noise, etc. We would look at that.
so anyway, we are going to see the design of the controller for the motor, DC motor, correct, in the end of the
Yes,
course.
yes, yes. Next,
So,
next, whatever we'll be discussing will be confined to DC machines only.
okay, sir. Can you just summarize one of the lectures that is going to come? Summarize how to estimate the parameters of the motor that only decide the controller
Yeah, yeah,
design,
yeah.
right?
Parameters. We will first discuss about parameters. Then only we'll go to controller design.
Okay,
We will
but
understand. We'll understand about equivalent circuit of a DC motor. Why there are different parameters. How can we understand from the field what are the relative values of those parameters? Why back EMF comes in armature, not in field? All those things we'll discuss. And yeah, thereafter we'll go to controller design.
okay, okay, okay.
Yeah.
Sir,
Sir, one
another
doubt,
question
sir.
I have.
Am I audible, sir?
Yes. Yeah. Someone was telling something.
Yes, sir. Yes, sir. Actually, during that induction machine, in the squirrel cage machines, which you have shown
Ah.
in the diagram, currents will be there in the bars,
Actually, your sound is not very.
right, sir?
Your voice is not very audible to me.
Okay, sir. Am I audible now?
Yeah. Yeah. Better.
Actually, sir, in the induction squirrel cage induction machine, the
Yes.
current will be there in the bars, and as you suggested, each bar will be offsetted by 360 by n into p by 2. So, how is
Yes.
the amplitude of current determined?
Amplitude of the current will be determined by uh, whatever is the. I left this from this tab or what? Oh no, I'm here. So let me share my screen. Yeah, just come back. So you are talking about the amplitude of the current, right? So we have seen
Yes, sir.
that we have looked at the induced EMF in different bars at different instants. So we know that this is the induced EMF at some given instant of time across a bar. A bar is simply like some something like this, some copper or aluminum conductor across which the voltage of 0.5 volt or whatever, it will keep on changing. This voltage or induced EMF across the bar will will keep on changing with time. So if we know the resistance of the copper bar, then simply dividing the induced EMF by the resistance will decide will tell you what is going to be the current. Or more accurately, if because any conductor will have some inductance also. Why inductance? Because if you inject some current, then there will be some flux which will be enclosing that bar, and any flux linkage means some inductance, because the inductance is nothing but flux linkage by current. So any conducting body will have some inductance also. So I have discussed that any bar can be represented electrically by a series combination of L and R, where R is the bar resistance RB and L is the leakage or the inductance of the bar. So if we know what is the voltage across it, that is EB at different time, we know the waveform also. This is a simple RL circuit. We could just solve it to get the current. And we have seen that because the slip frequency, the bar induced EMF frequency is quite low, so this omega L, whatever is the inductive drop, is very low compared to RB. So we could simply divide the induced EMF by the bar resistance in order to find the bar current.
Sir, in that case, usually whatever FEM model you have shown is a 2D model, right, sir? So we need
Yes.
to run it as a basically open circuit bar and find the voltage across the bar, and later we need to short it with a resistance and pump the equivalent
No,
current.
you could do that the other way. You in some way that there are some so if you do it in FEMM, yeah, there is no other way but to do that. But if you do actually do it in ANSYS, they produce some flexibilities where you could define that all these bars, they are short circuited from both sides, and you could enable something called eddy current setting, because these currents are nothing but eddy currents. There are some flux linkages which is changing, that is inducing some voltage and that is inducing some current through that. So if you enable that, you could do that. In ANSYS, this ANSYS transient that gives this uh, flexibility, but if you are doing in some magnetostatic solver like FEMM, then yeah, if you have to get that, then you have to rely on that post processing. First you have to solve for 2D magnetostatic simulation at multiple instance, get the flux linkages of different bars, get the induced EMF, and then divide it by the resistance of the bar to get the current. That is the way.
Oh, in that case, that dynamic changing of current will not happen, right, sir?
No, dynamic current will not happen. Yeah, that is true. So certain dynamics can be still looked at, like if you do the magnetostatic analysis at different instance, say you define all this by some r cross, you define it by r dot, and you
Hmm.
do it similarly you do it for other windings also, and you keep on varying the time. So for time instant 1, you solve it, you get the b distribution in the year gap, you store it. Then time instant 2, you get b theta. So time instant 1, you get b1 theta. Time instant 2, you get b2 theta. Similarly you take do the thing for complete cycle or more cycles, whatever, b3 theta, bn theta, whatever things you do. Now at a given instant, you calculate what is the flux linkage of a certain bar, psi bar 1. Similarly, at this given instant, you can get the same thing for psi b2, psi b3, psi b4, all these things. Then you could do the same thing for the second time instant, third time instant, fourth time instant. Now all these vertical things, psi b1, at different time instants you could plot them. Psi b2, you could plot them with time, because all these are different magnetostatic simulations for you, and all these are coming post processed results coming out of that. You could plot that like psi b1 with time. You could simply plot this t1, t2, t3, whatever you got. Now you have psi b1. You can estimate this resistance and inductance from FEMM or from hand calculation. So that by that thing you could, once you know this IB1, some current, some flux linkages, you could also get the EB1, that is the induced EMF. Now you can divide the EB1 by the impedance to get the current. Now after that you could write that KVL and KCL equation in the end rings to get the end ring currents also. End ring currents for all these different instance with time, or all these different all the end ring currents at a given instant, and then repeat the same thing for different instance. So all these things can be done from magnetostatic also. Thing is, you have to get into deep and do all this analysis, and that will actually give you more insights into how things are happening. If you just give it to some software and that does it for you, then you lose insight. You do not know what is coming, why is that coming. You are clueless unless you are clear about all these uh, intermediate steps, how it is happening.
Oh, thank you, sir. Actually, what I understood from you is basically full rotation of 360-degree needs to be divided into smaller angles, say uh, in between of 10 degrees or so, and we need to
Yes.
compute each flux linkage in that particular things. And once the
Yes.
flux linkage is computed, we need to regenerate the flux linkage, and we need to
Yes.
differentiate to get the back EMF. And from the back
Yes.
EMF, we can find the current, and later we can pump
Yes.
the current to generate the torque. Is it
Yes.
correct, sir?
Yeah, this is somewhere correct.
Okay. Okay, sir.
Yeah,
Thank you, sir.
but it requires a lot of in between steps, like if you have an induction machine type of a case, then you have to do it for different instance of time. At one instant your magnetic field may be somewhere, as shown here, downward. Next instant it will be something somewhere else. Now next instant the conductors will also rotate by some angle. So there are complications. So if you sit and carefully handle all those things, yeah, it is possible, whatever steps
The,
you told.
you mean to say that it will be a function of theta and time, both, sir?
It will be a function of time only, but the conductor, like how to get, suppose you have b theta. So suppose, where do I have some free space? Suppose at any given instant of time you get, this is b, this is time instant 1, this is along the air gap circle at different theta. Now say I am only considering the fundamental of it. Actually it will be that all those notches that you have seen, all those will be there. But suppose you get this bt1 as a function of theta. Now you have to get the flux linkage of a certain coil or bar. Now how to do that? You have to know what is the location of that bar at that instant. Suppose you are at t equal to 0, or you are in the beginning, this B19, you know that B19 is there at 0 degree. That means B19 is here. B19 here means you have to integrate this B over this thing. So so for conductor, how to get that? Suppose I think about this. Okay, so for conductor you have to integrate from minus pi by 2 to pi by 2. Suppose you have a conductor which is at theta equal to 0. Now you have to integrate the b from minus pi by 2 to pi by 2, and that will give you the flux linkage for that conductor or bar. So in this case you can see that B19 is at theta equal to 0, and minus pi by 2 it is minus peak, and pi by 2 it is plus peak. So if you do the integration, this area is equal to this much area. So there is no net flux linking the B19 coil. Similarly, suppose you do it for some coil which is here, say B25 or whatever, this is here. So for getting the flux linkage for this coil, you have to you have to do integration from, say, whatever is this angle, say theta 1, you have to do integration from theta 1 minus pi by 2, say here theta 1 minus pi by 2 to theta 1 plus pi by 2. You can see that it actually it is all positive, so you have maximum positive flux linkage. You got it right?
Yes.
But
Yes, sir.
suppose a conductor, say B19 is at 0 degree at T1 equal to 0. Now if you do the same thing, say BT2 with theta at different instance, now it will rotate by some angle because it is a rotating field. So the
Mm.
sinusoid that you will have will shift by some angle, right? Now
Yes.
the rotor is also rotating. That means
Mm.
B19 will also get shifted by some angle and come to some other location, say here or here.
Mm.
So in that case, while integrating, you have to calculate what is the updated position of theta 1, where theta 1 indicates the location of the bar. Because the
Mhm.
rotor you have in time instant you have moved by some time t1 to t2. Within that time interval t2 minus t1, what is the angle by which theta 1 has moved? You have to calculate that. So this will be the new theta 1 at the
Mm.
at the new instant. Theta 1 minus pi by 2 to theta 1 plus pi by 2, this whole interval, to get the new flux linkage of the same bar at different in the different instant, in the next instant. And the same thing you have to do for all the conductors, and then that will give you current. Yeah, now I think you have got.
Yes, sir.
Okay.
Thank you.
Anything else?
Sir, I have a doubt.
Okay.
Sir, based on the leading and lagging, how we can say that the power is transferred from the leading to lagging?
So this can be answered in from the basic power flow equation also. So suppose I, so I'll erase some things here.
Sir, from voltage perspective, you are talking about, you are going to
I'm
like
going to
to
speak. I'm going to speak from, say, so see what is there in a machine. There are two
fields.
electrical circuits, right? And there is
Okay.
they are coupled by some magnetic field. That means
Yes.
you could you could get it you could represent it roughly by two EMF sources, because EMF will be there in both the windings, some E1 and E2, which are basically magnetic field. That is,
co-
the coupling can be
Connected through an
represented by the
inductor.
mutual inductance.
Yes, yes, sir. Okay.
So if this is leading by some angle delta, then that
Okay,
means,
sir.
if you solve this equation, you know
Yes,
that
sir. Yes.
active power flow happens from this side to this side. This is
Okay.
the analogy you could have.
Okay, sir. Thank you so much for the insight, sir.
Okay, thank you. So let us close.